was some of the first physicists or scientists to study pressure. And here you can see some of the value here. Okay, see. So this is his portrait, and he was the one that invented the barometer. Okay, and this is a very important tool to measure pressure, and a very simple one. You just fill in a tube with certain liquid and then put it upside down and put it in like this. Then when this thing goes down, here will be a vacuum. Okay, and as a result, the water will drop down until it stops somewhere. And here, this much water here is actually supported by the atmospheric pressure. Right? It is supported by the atmospheric pressure. This means if you have some liquid with less density, less density meaning the volume will be larger, right? Then the height of this tube will be higher. Okay, meaning if you, for example, here usually we use mercury, right? Mercury. Then we measure this length here, this height. We find that this is 76 centimeter under atmospheric pressure. 76 centimeter mercury. That is already a measure of the pressure of atmospheric pressure. 76 centimeter mercury. And we will learn how to calculate this afterwards. This is a unit of pressure. So if you let's say you replace this by water. Okay, by water, and we know the density of water is much less than mercury, then the result is this water column will shoot up higher. And instead of 76 centimeters, it is now 10 meters, 10.3 meters height. Okay, if this is water, and that much water will be supported by the atmospheric pressure, and we will learn this later. Okay, so this is a very simple tool to measure pressure. And actually, in daily life, we have been using this idea, the atmospheric pressure. Here, you see a glass filled with some water, and we want to drink it using a straw. So what happens usually is that we suck the air out of this straw here. Okay, so once we suck out the air, this part becomes vacuum. Vacuum means nothing here. Then atmospheric pressure here will apply a force or a pressure on the water, and this will force the water into the straw. Okay, so how high this water column is will be supported by the atmospheric pressure. It depends on the atmospheric pressure. If you have a larger pressure, then it will support a higher column, water column. Okay. And this water column, the limit, okay, as a result, the water level will rise because the atmospheric pressure pushes this much water into it. And you find that the height of this water that can be supported by atmospheric pressure is 10.3 meters. And this is another figure that we will see a few times. Water. For mercury, this is 76 centimeters. And this sets a limit for the water that we can transfer to a tall building. A tall building, right? For example, let's say KLCC is so tall, but we cannot transfer water, transport water from the ground to a place higher than this 10 meters using atmospheric pressure. Right? So what we can do is you need to use a dynamic pump to pump the water up to a higher level, more than 10 meters by force, and by some extra energy. Okay, so this is a thing we deal with daily. So this is Torricelli, the scientist. And then another one interesting about the same time is Magdeburg. And Magdeburg is the mayor. Magdeburg is a city in Germany. And Magdeburg is a city. So the mayor of this city invented a Magdeburg hemisphere. And this thing shows the existence of atmospheric pressure. Why? You see, everyday life we are experiencing the atmospheric pressure, but we don't feel anything. And we don't know that there exists pressure because we are already familiar with the pressure applied on us. So to show this is actually you need some very genius thinking, right? So here is Magdeburg. Let me show you. So this is the classics drawing. This is the Otto von Guericke, I guess. Okay. So as you can see, we make it. Okay. See, it depicts the hemisphere here, the Magdeburg hemisphere. Okay, here. So what happened is, initially, these are two hemispheres. Okay, so we put them together, attach them, then we suck the air out of this using some methods that I will show you afterwards. Okay, suck it out. Then the inside, this is a hollow sphere. Then inside becomes vacuum. Okay, now we get a lot of holes. Try to pull this apart. We find that even these many horses could not do that. Okay, and this is intended to show the existence of atmospheric pressure. Because atmospheric pressure is pressing in. Okay, press these two hemispheres together and prevent the horse from pulling them apart. Okay, and this is a very nice demonstration of the existence of atmospheric pressure. And here we have a nice video demonstration, physics demonstration, and we can see how it works. And so there is no noise, no voice here. You can just watch the thing. Okay, now look. So this is a vacuum pump. And this is the Magdeburg sphere. See, you can pull it apart easily, two parts of the sphere. Then we connect it to a vacuum pump. Okay, then we suck out the water using vacuum pump. So as you can read on this meter here, you see the pressure is going down as we remove the air from the hemisphere. You see, it's going down, right? And then when it is low enough already, the pressure, let us detach this and let's see what happens. Then we try to pull them apart. You can see this is impossible. Even if you have many horses to pull this apart, it's impossible. This shows the strength of the atmospheric pressure. And now you see we try to release the thing. So we let air move into the hemisphere again. And see what happens? Then you can pull it out easily. Okay? So this is actually a very nice demonstration of the Magdeburg sphere. Atmospheric pressure. Okay. So the next thing is, submarine. Actually, we have been using this idea in submarine also. Let me mute this first, to mute. I don't know how to mute everybody. It's too noisy. Easy. Okay, now it's gone. Oh, I understand. I forgot to change the setting. That's why the noise started to do that. Okay, never mind here. Okay, a submarine, for example. When we produce a submarine, we need to be careful. No? The body is strong enough. Whose thing is that? Hello, can all of you mute your mic?
Sir, no one is on their mic.
On what?
No one is.
Oh, the YouTube. Sorry. Too bad. Okay. All right, so submarine. Okay. we need to make sure that the body of this submarine is strong enough. Why? Because when the submarine submerged into water and into a very deep sea, then you see that the pressure of the water will try to push to crush this the body of the submarine into it. Okay. Therefore, if the material is not strong enough, then the person inside will die. Okay. So this is one of the principles that we need to understand when we produce a submarine. And there's another issue regarding submarine. Is that how can we let the submarine dive down into the deep water? Okay. And that part will be making use of the idea of Archimedes principle, the buoyant force. And that part we will discuss in the next week. Okay. So this is again, we can see that pressure in work. In the first case here, we have pressure due to air, the atmospheric pressure. This case here, we have pressure due to water, seawater, fluid. And then pressure can also be due to radiation. Right? Radiation looks like there's nothing, but actually can produce pressure also. And here, I can show you a very interesting thing. Call this the solar cell. See, solar cell. So as you know, when we want to do this kind of star traveling, you need to bring in a lot of fuel with you, right? But then we cannot bring too much because that will limit our traveling power, how far we can travel. Therefore, one way is either you can collect the dust, interstellar dust, you use it as a fuel, or there's another way is this. We make use of the pressure due to the radiation of the solar. The radiation, when it hit on this solar cell, it will produce a pressure. And that pressure will hit on this area, will produce a force. And that force can accelerate this solar cell. And so this is just some imagination. But indeed, pressure, the solar cell has certain kind of pressure that we can utilize. And so this is just an artist's depiction. And we are yet to successfully produce this kind of thing yet. And so this is a very short introduction on what we can do with pressure in our daily life or in our technology. Okay, so here is what we want to study in this chapter. The density of, first we study the density of materials. Why? Because we need to use it to calculate pressure later. Understand pressure that is exerted in solids and fluids. For the pressure exerted by air molecule, the movement of air molecule, we will study that in the chapter number 7, kinetic theory of gas. Later we'll do that. Here we only do the solids and fluids for water. Okay, so in this chapter also we need to understand how the various apparatus are used to measure pressure. Okay, so the apparatus, and the last part is Archimedes principle. We are going to use this to explain the buoyant force. That is the principle at work in a submarine, how a submarine can dive into deep sea. And this part we'll study in the next week. Okay, so let us start with density. This is a simple one. Everyone has studied this. So here we have the definition, mass over volume. Okay, so this is a property of matter. The reason is it means that if we have a certain kind of material, the density is fixed. It has a certain density. Okay, irrespective of how much material of this metal you acquire, the density is always the same. It will not change. And it is a measure of the concentration of matter. And we can compare different kinds of matter. We have 3 types, we know: solids, liquids, and gas. 3 types. So if we compare the density, and as you can see, for solids, usually it is much higher than liquids, the density. And for the density of liquids, it's much higher than gas. Therefore, this shows the concentration of matter inside these 3 kind of material, these 3 places. Okay? So in solids, the atoms, they are arranged closer to each other. Therefore, we can find more material within a given volume. That's why it is heavier. Let's say given 1 meter cube. you will have a heavier weight. With the exception of mercury. Mercury is a fluid, but then it is a kind of metal. You see, so it has a very large density compared to other kind of fluids, liquids, okay, and air. So one nice thing here you can see is the density of water. We know that it is 1,000. Okay, 1,000. So such a nice number, we will utilize it as a reference later. We use it as a reference for our density, and we can introduce another quantity, so-called the specific gravity. After this, so here we always on our level we assume that the density is a constant under specific condition. As for example, here we have atmospheric pressure, and then the room temperature. Okay, so we assume that the density is almost constant under this kind of condition. Okay, so one important thing about density is the unit. This is the SI unit, kilogram over meter cube. But then this is such a large unit, 1 kilogram and 1 meter cube is a very huge volume. So usually in the lab, instead we use gram over centimeter cube. Now we measure the weight in grams and the volume in centimeter cube. Therefore, we want to introduce another unit, a gram over centimeter cube. But then you need to know how to convert between gram centimeter cube to SI unit kilogram over meter cube. So here I deliberately showed it once and for all, very clearly to you, because many students make mistake in this conversion. You see on the left hand side here, you have gram over centimeter cube. On the right here, kilogram over meter cube. And it usually looks like that. Gram is much less than kilogram. Therefore, students can make mistake here. They usually write 1 gram over centimeter cube equals 0.001 kilogram over meter cube, because they just convert gram to kilogram, forgetting the volume underneath here. Okay. So here I show you, gram into kilogram is 0.001, but don't forget about this centimeter cube. Then it gives us 0.01 meter cube. Then you need to cube it, power 3. Okay, you produce a much smaller number in the denominator, and therefore the final answer is 1,000 kilogram over meter cube. Okay, so remember this. It's a very important one. Don't make this kind of silly mistake again in the exam. Okay, remember this. So now let us look at this. Just now we already said, right? Because the density of water is nice, 1,000, and also we can get water everywhere around us. It's a very abundant material everywhere. Therefore, we want to use it as a reference density. Why we want this? Because sometimes in the lab, we don't even need to really measure the density of a substance. To measure the density, we know we need to get certain amount of the material. We need to measure the weight. We need to measure the volume. But the measurement of volume is sometimes difficult, and also it can create a lot of errors. So we can invent some very clever method to find out the density of that substance without really measure the volume and the mass, because we know the density of water. So there's some very nice method using the buoyant force, and that is the topic of the first lab for this method. And next week, I think we shall start the first lab already, next week. And you will make use of this idea, specific gravity, and also buoyant force. So after we finish buoyant force, we can do the first lab. So in that lab, we don't need to measure the density of the substance directly. Now we just make use of the fact that we know the density of water, 1,000, and then we can use it to obtain the density of the substance. Okay, so this is the purpose of introducing this quantity, specific gravity. We use the density of water as a reference. Okay, and this, of course, when the same thing divided together, you don't have unit. Specific gravity has no unit. Okay, anything up to this point? Any question?
No questions, sir.
No, okay, so this part should be simple. So let us now look at pressure now in solids. This is the definition of pressure. So we look at the normal force acting per unit across an area. Right. So actually, pressure is the average force over some area, average force. Why do we need this average, this idea? The reason is this. Up to now, maybe you learn about the mechanics, right? In mechanics, you have just one material, or let's say one block of things. So you assume the force, when you act on it, it is acting on this, the whole thing. So the whole thing just moves. And you don't care where it acts, okay? But then when you think about pressure, now it is important to think about a thing. You could have just the force acting on just one point. And this force will be distributed, the whole thing will start to feel the effect of this force. So the force will be distributed across the whole thing, and the whole thing feel an effect. So instead of talking about this force, we need to talk about the average force. So we need to think about pressure, because this force is, the effect of this force is distributed over this area. So the whole thing feel the effect of this force. That's why we divide it over this area to find the pressure. So even though you have a large force, for example, a very large force, but if the area it applied on is very large, then the effect of the force becomes too small. And the correct concept to use to describe this is pressure. Okay? In mechanics, usually we think about point mass, not the mass. Think of this as a point. When you talk about gravity, this is the sun, this is the earth. Actually, we don't think about the volume of the size of the sun and the earth. We just think of sun as one point, the earth as one point, and when we think about the force between them, we consider the force. So when you're talking about mechanics, you don't need this. But here, when we're talking about matter, you need to think about the size of the object, the real size, and that will affect the effect of this force. Okay, that's why we need to think about pressure here instead of just force. And we will see that later. For example, if you have a wire, a wire has certain area, right? And this area will affect the strength of the wire. And you will affect the strength, and that is part the material of chapter 5. We will consider this. Okay, so when you consider the matter as with a size, you need to think about pressure and some other thing. Okay, so this is the normal force. Why? Because when you think about the thing like this, this is the material. Right? You apply the force like this. From now, you already learned in mechanics, you can divide this into two components: horizontal component, vertical component, the force. So only this vertical component is going to push the object onto this table, push it down. This one has no effect. This one will just push it here. So you need to think about the normal component only. This component will produce a pressure, not the horizontal one. And so this is a simple idea of normal force. Okay, so as you can see in solids, because the area is not important, we need to average the force on the area. Then the orientation of the object will affect the pressure exerted by the weight of these solids. For example, here, let's say we have two pieces of bricks, right? Identical bricks. They have the same weight. But when you orient them differently, this one has a larger area in contact with the ground, this one a smaller area. Then you find that the weight when distributed over this area, they produce a different effect. And this here, the effect is larger. That's why the pressure is much larger than P1. And this pressure exerted by this orientation is larger than this orientation. Okay. Another thing to see this is a knife. Right? We have a very sharp end of the knife. For what reason? Because you can apply a small force, but then because the area is so small, the effect of this force becomes very large. Okay? And this effect is measured by pressure. The pressure will be very large, and such a large pressure will cut through the surface of a very strong layer of things because of the large pressure. However, if you have a blunt one, you know the effect of the force is too small. Okay, so this is another idea. Pressure, you need to think about the area. We average the force over the area. Okay, so here is a simple example. For example, a chair stands on 4 feet, right? And each feet is an area of 10 centimeter square in contact with the floor. And the chair weighs 80 Newton. So here we can calculate the average of this force over the 4 legs. If you have 2 legs only, it means each leg will support more weight, right? But here we have 4 legs, so we expect the pressure should be lower. So we just calculate the thing. For example, weight of chair is 80 Newton. Total area in contact, because this weight will be distributed over the 4 legs. So here important, you need to be able to convert centimeter square to meter square, right? In this way. So remember, 1 centimeter equals 10 to the power minus 2 meter. Okay, so square it, you get a lot of 0.0. Huh? So in the end, you get this. So average force is the pressure. In the end, we get 2.0 times 10 to the power 4 PA, right? So question, how many significant figures you need to leave? So here actually this is 1 or 2 significant figures. We don't know, either 1 or 2. So here I leave it to 2 significant figures. I'm still consistent with this. We assume this is 2, this is 2. So from the rule in chapter 1 for division, we look at the one with the smallest significant figures and we follow it. So here I'm assuming this is 2 and 2. And I keep this 2.0, 10 to the power 4 Pascal. Okay. Okay, if not, so about half an hour. So let us do one very simple exercise. And also now I unlocked the instant. You can sign in now. Unlock. This is the last time. I unlocked that. And about your practice question, I found that some students either they totally do not attend the activities, or some of them they sign in, attempt it, and then put some random number and submit it. We know that. Okay, I can see all the number you submit. So, and some of you attempt it, but you do not even try. So I think this is very bad, This is not a good attitude to do things. You might think that the exercise is simple, but then I think there's no harm, You just try it out. Okay, so you can go to your Moodle. Okay, under chapter 4. So let me chapter 4. Okay, so under chapter 4 here you will see that the first one, density and pressure of solid. Can you try to do that? This is a simple one just to test yourself. So I give you maybe 4 minutes. Okay, can you try that now? One more minute. Okay, are you done? Okay, so let us discuss. So this simple exercise, how simple it is, we try to learn a few things here from this exercise. The first thing is, for example, question 1, the conversion of units. You need to make sure you get it correct. And the second thing is the significant figures. And just a practice of chapter number 1. So as you can see, we learned a few types. There are two numbers here, 240, 3.0. Two significant figures, right? This is for sure. And 240 also, two significant figures. Oh, sorry, I didn't do this here. Okay, let me, if you finish attempt, already finished. Okay. 0, this is two significant figures. 240 also two significant figures, 2 or 3. Okay, so using the rule in chapter 1, when you do the division, you take the one with the least significant figures. Okay, so this is a simple exercise. We leave it 89, 8,900 significant figures. And you need to make sure you be able to convert the unit correctly. So this is the first thing we do. So even some simple like this, sometimes we can make mistakes. So don't worry, don't be afraid to make mistake. Now, since this is not taken into account. And the second one is, the purpose is this. Because later in your exam and also in your lab report, we are going to use the Moodle as a platform for you to submit the answer. Therefore, we have to follow the rules given by Moodle. We do not create Moodle, but we just follow the rule. So for very small and large numbers, sometimes you need to key in scientific notation. So you do the thing like this. As you can see here, a number like 2.568 times 10 to the power minus 4, you key in as this, using the E to represent the power 10, the 10, just like in your calculator. Okay, so you can try, if you use a small letter E, it is also acceptable, but I don't want that, because I don't want you to confuse with the exponential. So let us keep to capital E. Okay, and you don't need to leave any space in between here. Okay, and let me tell you, I emphasize, this is the standard where the Moodle will accept this answer. But sometimes I found that in the yesterday's answer, some students key in like this, times, using an X, 10, then power, they use the angle, the triangle, not pointing upwards. So let me warn you, those are the non-standard way of doing things. Sometimes Moodle would not accept that. Okay, do you get me? Those non-standard way of keying in things, that is your problem. You are responsible if you key in the non-standard one. I already tell you the standard one. This is the standard one in the box. You should keep to this rule, follow this. Okay, if you get it key in like this and it is wrong, then this is my problem, my responsibility. But if you key in other things and get it wrong, don't argue with me, okay? That is determined by the system. Okay, so I want to make this clear to you. And for the second part here, let us discuss a little. let me use the whiteboard. Okay, so here, as we said just now, right? If you have a needle, try to pierce through. Even though this is a very strong thing, if you use even if let's say you apply 15 Newton, if you use a very blunt one, it will not go through because the effect of this 15 Newton is distributed over a large area. So the effect becomes very small. Instead, you use a needle with a very small area, the effect becomes very large, tremendous. And that effect, we use pressure to describe it. And that is why it is necessary to talk about pressure instead of force. The force cannot explain this. Okay, so here, if you want to find the area, the maximum area possible for the needle, you need to solve for the thing like this. Okay, you take the force divided by the pressure. This is the breaking pressure. Actually, in material, we call this stress, breaking stress. Here, because we have not introduced this idea, we use the idea of pressure. Actually, we call this stress. So when you have a breaking stress, the thing will start to break down, to break apart. Okay, so here, let me see. Since as you can see in the numerical values given, this again 2.3, there are two significant figures. 15 also two significant figures. Therefore, you leave the final answer to two significant figures. Okay, so you can see you can type in a lot of zero, it is correct. But here it is a practice. Key in using the E, the scientific notation. Okay, so is it okay? For this part, a small exercise. Okay, so one more part, we are left in maybe 15 minutes. So let us do. Now from solids, pressure and solids, let us now do static fluids. Fluids includes liquids and also gases, right? So let us look at this. So for pressure in fluids, because fluids is different from solids. Solids, you cannot change the shape easily. But for fluids, it is malleable. It can take any shape given by the container. So the pressure exerted is different from the solids. So here is the formula. You learn this also, I believe. Okay, so the pressure in the fluid is given by the rho GH. Rho is the density of the fluid. So from G is the gravitational acceleration and H is the height. And from this, you can see that density actually is given by the mass of the object, right, of the fluid. So mg is the weight. So again, you can see that pressure is given by the weight of the fluid. And then now divided, average over some area where the fluid is acting on. And so this is the same idea. And we can see it easily here. For example, you have a container with certain water. And the pressure exerted by the water on this surface area here is you need to find the weight of the water, of the fluid inside, divided by the area, because this much weight will distribute over this area. So we can just find the mass using the density, right? Because the fluid does not have a specific shape, we need to find the total volume, and the density gives us the mass. So from here, the volume is just the area times the height. Then we use the idea of the pressure. The general definition is the force divided by the area. So the weight of water is just mg, and then we divide by the area, and we get this rho gh. Okay, so from this you can see, this is the pressure due to fluid. And the important thing is, you can see that density is the property of the material, G is also a constant, and the thing that changes is H. Because H will determine how much weight will exert on the given area. If you have more water, the depth is larger, then there are more weight acting on the surface area. Okay, so these are the property of pressure exerted by fluids. They are independent of the total area because we already average over the area. So talking about a small area is not important if you want to talk about pressure. Unless you want to talk about force, then area is important. Okay, so you can see that pressure in fluid increases with depth, because the deeper you go, there will be more wet above that level, and therefore the pressure, the force will be larger, and hence the pressure is also larger. Okay, for example, in this is water. In this level, all the weight of the water above this, the fluid, will act on this area, on this level. Okay, and therefore the deeper you go, more weight above you, and therefore pressure is larger. Okay, so from this we know, even though air is very light, but when we have a lot of air, the weight due to this air can also be very large. For example, in our atmosphere, okay, the thickness of our atmosphere is, I think, a few kilometers. So there is a lot of air molecule in this this thickness. Therefore, the atmospheric pressure can be very large. This is what we are experiencing at the ground, on the sea level. Okay, and you can see that also from this expression, rho GH. G is here. G is gravitational acceleration. Why? Because gravity pull the mass down and causing it to have a wet. So if you go to a wetless condition, for example, outer space, when you have a space shuttle revolving around the Earth, a satellite, okay? So that satellite, the thing inside will be under a wetless condition. So we will, the thing that inside will not cause any pressure because it is wetless. G is 0. Okay? Therefore, in a space shuttle, you need to pump air inside the cabin. Put more to increase the pressure. That pressure is due to something else. It is not due to the weight of the air, okay, in outer space. Otherwise, if we don't have the normal pressure outside us, our blood pressure vessel will burst. Okay, our blood vessel inside, blood is moving inside, right? And then there has some pressure. If the outside pressure is not the same as the pressure inside the blood vessel, then the blood will burst. Our vessel will burst. Okay. Therefore, in outer space, we need to make sure that our surrounding has the same pressure, normal pressure as we have here. Therefore, we have to pump in a lot of air to increase the pressure, and that pressure is not caused by the wet, not caused by gravity, but by Brownian motion. Now, we will study that in chapter number 7, the kinetic theory of gas. Okay. So now let us look at one example. Now, here we have a cube, 0.20, about 20 centimeters each side, floating in water. Okay, and then only 0.15 meter of this is below the surface of water. Okay, and this is density of water, we know is 1000. Here we want to calculate the pressure of water acting on the bottom of the surface. So here, even though the atmosphere here is exerting a pressure on the cube, but here we just are interested in the pressure of the water, pressure caused by the water at the bottom surface. It means at this point. Okay, and because there is a pressure here, the pressure is caused by this amount of water, this depth of water, and they will cause a pressure underneath here, and that pressure, if we multiply by the area, will cause a force. A force will be acting on this object and try to make it float. Okay, so this is the origin of the upthrust force on the object when it is floating underneath water. This upthrust force is produced by the pressure of water. Okay, so let us calculate this upthrust force. How do we do that? Pressure due to this depth of water, 0.15 meter. So we know if you want to calculate the pressure at this level, then you need to know the height of water, because this much water, the weight of this much water will produce a pressure on this level. If you go deeper, then there will be more weight. Okay, so up to this level, only 0.15 rho GH. That is the thing you use. Okay, so here we calculate the pressure on this level. So this much water on it, 0.15. So here rho is the density of this fluid, g gravitation acceleration. This produces the weight of the water, and h tells us how much water is available. So here 0.15 meter. When you calculate this, you get this number. This much pressure is acting on this level. Okay. So here, if you want to report, this actually is the intermediate process. But if you want to report, so here we follow our rules. 9.1 is actually 3 significant figures. This is 2, and I assume that the density of water, this one is a constant. So we just use 2 decimal for our final report of answer. This is the answer for part 1. Okay, we keep 2 significant figures. Okay, so now this is the first step. We find the pressure. Now, next step, find the upthrust force. We want to find the force. So this is the second step. So to find the force, you take the pressure acting at that level, multiply by the area of the object and the underneath area, which is 0.20 squared. Okay, and for this step here, we want to keep one more significant figures. As we learned this before, keep one more, because we don't want to have the round off error. Only then we get, in the end, we round it off to 2 significant figures. So this is our final answer. So again, if you don't do this, for example, here you use 1.5 instead. You use this final answer, then what you get is 60 Newton, slightly larger than this. So that will cause some. Any question on this?
Good, sir.
Okay. So almost time. Actually, I have one exercise, but I think we'll do it next week. I just want to discuss one thing with you, because many students, after doing the exercise number 3, plotting the graph, you will certainly get a different answer from the solutions, right? Because everyone will have their own plot of graph, a different graph. So your answer will be slightly different. And how do you determine whether your answer is possible or not, is acceptable or not? So let us explain it this way. If this is the solution, solution is, this will be plus 1. This is the minus delta y. This is a solution. Solution is y plus minus delta y. Okay, so using this idea, we know that we can draw an error bar. Okay, now you know you have this idea of error bar, so I can use the error bar. This is the error bar. This is the average value, the maximum, the minimum, the error bar. So this is the solution. Answer given by the solution. Then your answer will be slightly different. For example, if your answer is, let's say, x plus minus delta x, then you can plot your answer here. You can compare it here. For example, let's say this is your x, then you have another error bar. This is your error bar, x plus delta x, x minus delta x. So you can compare these 2 figures, and you learned this before, right? This is your error bar. You can compare. There is an overlap between these 2 things, and a quite large overlap. Therefore, your answer is quite good here. I could say that. This is one way how you can determine whether your answer is acceptable or not. You see, your answer is within the error bar, okay? And not so, and they have a lot of overlap. If your answer is totally the same, you have an exact overlap. Right? An exact overlap meaning your answer is exactly the same as the solution. But then if you have an answer like this, you see, then this is certainly not good. This is outside the range given by the solution. This is not acceptable. Too bad. Okay, and something like this, maybe something here, then this might be too far away already. Okay. So in this way, this is one way how you can decide whether the answer is good or not, acceptable or not. And of course, I want to emphasize in the exam, we will allow certain tolerance. Usually, for example, this is the final answer, then I will allow certain tolerance in the last digit, maybe 0.0123 or something like that, depending on the situation. They will allow for this in the exam only. And the exercise, as you see, as you notice, I emphasize on the exact way. Because exercise, we don't need to worry about losing marks. So you can practice what you learned before. Right? But exam is a different condition, quite stress, under stress condition. The student can make careless mistake. Therefore, I will allow some tolerance. And this is only for graph. Graph can be certain different. Everyone has a different graph. So this is the first method. And the second indication, this is the first indication. Second indication is you can take your solution minus the standard solution. Your answer minus the solution, and then you can take this ratio. This, we call this percentage error. Okay, so actually you are looking at the difference between your answer and the standard solution and divided by the solution, and you calculate how many percent. If usually this is, we say less than 5%, then this is almost acceptable, quite good. If you have something like 15%, and then this is too large. Okay, usually we use less than 5% as an indication of the correctness of your answer. Is it okay? This is the two way. If you don't know how to decide whether your answer is good or not, you can try to look at these two aspects. Both is what we have learned using one, the error bar, and using two, percentage error. And also plotting this graph, actually you can, for the table, you can make use of the Excel graph and find the best fit using Excel graph. But we don't have time to go into that. So later, maybe next week, if we have chance, I can show you how we can do that. Is it okay? Any other question? Otherwise, that will be the end of this class, today's class, okay? Okay, then goodbye. See you next week and do your homework. Okay, goodbye. Thank you for your attention.